All right, we have reaction video number 32 here, also known as 2 to the 5th. So, not ever sure where to put myself. I'll leave myself over here, I guess. Um, so, I'm guessing it's a review since that's what it says. So, here we go. Ooh, look at that.
Hey there, everybody.
Perfect
Mr. Martin
handwriting.
with you, and today we're reviewing momentum, including conservation momentum and the impulse momentum theorem. So the way that I'm going to kind of organize this is by comparing what we do with objects with what we do with systems.
What is going on here? So, it's like an accelerated video with voiceover? Oh, this is so cool. All right, let's keep it going.
So to find the momentum of an object, we simply multiply the mass of the object by its velocity. Keeping in mind that things that are moving in different directions need to have different signs for their velocity.
Cool.
To find the momentum of a system, we simply do that for all the different parts of the system and then add the parts up. So momentum of thing 1 plus thing 2 plus thing 3, etc.
So it's really interesting to think about things in physics that don't do that, right? So if you've got a system of particles made up of a whole bunch of particles, you want to know the system momentum, add up all the pieces. System energy, add up all the pieces. The system mass, add up all the pieces. The system angular momentum, add up all the pieces. So that idea of, blanking on the word here, that idea that we can add it all up is super, super important. But it's interesting, right? There's subtleties, like that energy piece, right? To say that every individual has a potential energy is not quite right? So actually, it's pairs of things that have a respective potential energy, let's say electrostatic potential energy, or maybe gravitational potential energy. So you add up everybody's mass, then you add up everybody's interaction. But still, the idea that you just add the interactions, I think, is totally legit. So this idea, I wonder if students ever get tired of it, right? Like, well, duh, of course. So I do think that it's interesting when it's just an obvious choice for students to make versus, something subtle. So here, just add it up. Of course, it's a vector addition, so it gets a little bit more complicated, but otherwise really interesting. So first law, I wonder if it means Newton's laws here. We'll see.
etc., etc. And so, kind of going back and reviewing what we know about physics so far, we first defined Newton's first law, and we said that when there are no forces acting on an object, or when the forces are balanced, in other words, when the net force is zero, the velocity of that object is constant. And so, in a system of objects, if the net external force is zero, then the velocity of the center of mass is constant, and the momentum of the system is conserved. And so that's kind of a way of expressing Newton's first law for a system of objects. Newton's second law, we took acceleration equals net force over mass, and we kind of did a little bit of algebra to it to get the momentum impulse theorem, which...
Sorry, I'm just in love with this like spontaneous, super fast writing. It's just incredible handwriting. Is it a font? No, these two T's are different, right? So look at this T and look at this T. It's not a font. He did actually do all this work. And it's like he's pausing it. Man, this is so cool. I really, really like it. We've talked before about like hiding things and slowly revealing them. And instead of just boom, here's the answer. It's like doing it all out in the order that he wrote it. Sorry, I'm just kind of stuck on that. If you've watched any of these, I probably was watching for this. So its momentum is constant. Momentum is conserved. If the velocity, it's because there's no change in mass. And so again, so often we don't have any mass changes in these early approaches to these problems. And for there to be a mass change, frankly, in most systems, the system has to change, like something has to come and join the system. And so usually we're talking about a very known, defined system. The mass, of course, can change if you have some interesting nuclear reactions going on, but we tend not to be talking about that stuff early on in the problem here. By the way, at some point I made some crack about how all energy comes from mass energy. And they said, what are you talking about? We get calories from food. And I was like, yeah, how do you think you get calories from food? It's mass energy. It's just so small. The amount of mass that changes is hardly anything. And so we don't tend to calculate it that way. Boy, there were some people who really didn't like that. So my question for you, dear viewers, Does all energy come from mass energy? Because obviously in nuclear energy, absolutely yes. People are like, oh yeah, we got all this energy because we lost a little bit of mass. Well, that's actually true of all chemical reactions, in my opinion. So I think it's truth. That's why I ask you about it. Anyways, that took us on a little journey there. Let's get back to this.
which is that impulse, or F delta T, is equal to the change in momentum. And of course, we can also find the impulse by finding the area under a force versus time graph. So the same thing would be true for a system of objects, only the net external force would be the external force on the entire system. And so we can't figure out the force on a single object within a system if we only know information about the system as a whole. We're going to look at an example of that a little bit later. In the Newton's third law, the force exerted on A by B is equal to the opposite of the force on B exerted by A. We found that the impulse exerted on A would also have to be equal and opposite to the impulse exerted on B, and that led us to our expression of the law of conservation of momentum. Because if
A couple of really interesting things. First, because I just can't help myself. Anytime I see Newton's three laws, I remind you of the way I think about it. I start down at the bottom. Third law, things swap momentum. Second law, knowing the rate that they swap might be interesting. First law, if you don't swap momentum, you're boring. So that's how I think about these things. It's all about momentum swapping, but it's connected to something that he said. He just said, and we found that the impulses need to be the same. What's fascinating about that is it's not that magically these two integrals end up being the same. Oh my God, I integrated the force over time for the first particle, and I integrated the force over time for the second particle, and miraculously I got equal and opposite answers. In fact, millisecond by millisecond, nanosecond by nanosecond, they have the exact same term. So it's not so much that the integrals are the same, it's that the integrands are the same. And if the integrands are the same, then the integral's the same. Well, with this extra negative sign. So I find that really, really fascinating. But I really love how he's building this up, right? I mean, it's obviously a review. It starts out, it's really hitting the highlights, just doing a fantastic job of hitting the things that are most important when thinking about why do we study this? How can we make use of it?
if one thing loses has to equal what another thing gains, the
Love
total has to remain constant. So let's do one example together real quick in which we can kind of illustrate a couple of these different things.
I love this.
And tie the object and system
Sorry.
view together a little bit. And so here's our situation. We've got a 2 kilogram blue cart.
Whew, man, if somebody ever says, okay, here's the situation, I just can't help myself. I just start thinking about Fresh Prince lyrics. So that way you know how old I am. Let's just pause for a second before he goes crazy. 2 kilogram blue cart moves at 10 meters per second. 10 meters per second, that's like 30 miles an hour. Okay, so that's fast. 2 kilograms. So what is 2 kilograms? So half a gallon. It's like somebody chucking a half gallon milk out of a 30 mile an hour car towards a stationary 3 kilogram red cart. So 3 kilograms is approaching now a gallon of milk, let's say. After colliding, the red cart has a velocity of 8. Ooh, notice that there's something missing in this statement. What's missing is whether they stick or not. Cool. Let's watch out for that.
That's moving at 10 meters per second towards a stationary 3 kilogram red cart. And then they collide and smack into each other. And afterwards, the 8 kilogram cart's moving to the right at 8 meters per second. And we want to first figure out what happened to the red cart, what impulse was exerted on it.
Cool.
And then also, what's the blue cart doing after the collision? Like, how fast is it going? And so, to find the impulse on the red cart, remember that impulse is equal to change in momentum. And so, the F delta.
So I just want to pause here for a second. So for those students who have in their head that impulse is this integral of f dt, this problem doesn't give you anywhere near enough information to set up that formula, that integral, right? The forces are not clearly defined as some weirdo contact force, but I just love how he says, well, it's this, but good Lord, it's also this. I mean, this is going to be easy to calculate. So let's just jump over the scary looking integral and do this. I love that.
F delta t expression is not going to be really helpful here because I don't know how much force was exerted during this.
Exactly.
But I do know the change in momentum of the red cart. So when we find impulse, like when a question asks you just, hey, find the impulse, we have to remember that there's a few different ways to do that, and we have to be smart enough to figure out which way would be appropriate for that situation. So
Awesome.
here, since I know what the red card is doing in terms of its velocity, I can find its change in momentum. That would be the impulse. And so change is just final value minus initial value. So the final momentum of the red cart would be like 24 kilogram meter per second, or 24 marks. The initial was 0 because it lost. And so just
24 marks.
24
Love
marks
it.
minus 0 would be 24 marks. When we write our answers down, we need to include the direction. And so let's be specific that that's 24
Oh,
marks
love that.
to the right.
Love it.
You can also think about that as being a gain of 24 marks.
To the right.
So when we find the velocity of the blue cart, there's a couple different ways we could do that as well. First, we could just use the fact that the momentum change of the blue cart has to be the opposite of the momentum change of the red cart. And so we could just say that the delta P for blue has to be negative delta P of the red. And so since the red cart gained 24 marks, the blue cart must have lost 24 marks. That's got to be true in order for Newton's third law to be true. And so the original momentum of the blue cart was like 20 marks.
So I'm intrigued by how well he is doing his voice over the handwriting, right? Just there, his handwriting got a little bit ahead of his story. Now I'm wondering if he's like hitting a pause button while he's doing this, or if when he wrote all of this, he sort of thought, oh, I'll bet you this will take me about 5 seconds, so I'll just pause. That's what's not clear to me at all, right? Just there, his momentum calculation got a little bit ahead of him, but it's I've praised this sort of multi approach of video and audio and written text. Super, super cool.
If I then add negative 24 marks to that, that leaves me with a final momentum of negative 4 marks.
It goes backwards.
And then dividing that momentum by a mass would give me the velocity. So negative 2 meters per second. And then realize we need to clearly indicate that that's 2 meters per second to the left.
Love it.
The second method to do this is to use conservation momentum. Since there's no indication of an external force here, I can claim that momentum is conserved. So the momentum of this system would simply...
So what he's doing, first of all, that was super awesome. Loved the stuff at the bottom here, where I mean, it's just great, and really saying, oh, to the left. Love the units, by the way. That's super cool. I've been saying that we need units for momentum forever. So this second method to me is not a new method, right? So my thing's in the way. This right here is saying that the momentum is conserved. So he's just going to have different terms on different side when he does this. So let's see how he connects method 2 to method 1.
would simply be the 20 kilogram times meter per second that the blue cart originally started with. There's nothing else in the system moving before the collision. And so write a conservation momentum equation for after the collision. Like the momentum of the red cart plus the momentum of the blue cart has to equal 20 marks. And then just algebraically solve for your missing blue velocity. And so we find the momentum of the red cart to be 24. The system has to add up to 20. And so the momentum of the blue cart must be negative 4 in order for that to be true. And then dividing both sides by the mass would give you the same negative 2 meters per second, which we should clearly indicate is 2 meters per second to the left. And so either of those ways would work if all we cared about was how fast it's going. But that's an illustrative example of how the law of conservation of momentum comes from the impulse momentum expression of Newton's third law. Because what's gained by one thing has to equal what's lost by the other. If I was interested in how much force was exerted on these carts, I would have to know how long they were in contact with each other.
Yes, that's much harder.
This doesn't give me information about the internal force, but in a situation like this, the internal force may not necessarily be something we really care about. We really just kind of want to know what the things do after they collide with each other. And so if I knew how long they were in contact, then I could divide the momentum change by that time to get the force, if I was interested in that.
So I'm just going to stop right there. I just want to back it up so that we have his stuff to look at here. So that last little bit, it's really interesting, right? So if one thing comes in and it takes a long time to interact with the other one before finally it recoils, it really does change the dynamics of where the things are. So this question never asked about where, neither asked force nor time nor where, right? But all three of those are going to be interrelated if you start to really provide more details. I love this. I love the handwriting speech coordination stuff. That's super awesome. Colors were awesome. Loved the units. Loved these two approaches, which to me were effectively the same. Basically, it happened right here. That the second method really is showing up right here in the first method. I think that's super cool. All right, everybody. Have a great day. And remember, physics teachers are awesome.